We want to look at how to multiply a matrix by a vector. So normally you would represent a matrix by a capital letter like A, and then the vector by a small letter X. We'll sometimes put an arrow on top of it to emphasize the fact that it's a vector. So the matrix, let's say we have a 2 by 2 matrix. So 1, 2, 3, 4. That's our old friend. And then we have the vector. Let's say the vector is 1, 2. So how do we do something like that? Uh, Traditionally, the matrix vector product is defined in terms of what is known as a dot product. So you have what is called a dot product of two vectors. Now, the dot product of two vectors, let's say u and v, is defined as, so let's say u has the components u1, u2, u3, and then v, sorry, I should have, so I say u and w, right? So yes, the u and w has the components w1, w2, w3. Then the dot product of u and w, here I'm omitting the arrows, we understand that they are vectors, is defined as u1 times w1 plus u2 times w2 plus u3 times w3. So that's the definition of the dot product. And the dot product is a number or a scalar. So sometimes the dot product is called a scalar product. And it is with this that we typically define the matrix vector product, like AX. And the way it's defined is you take the first row of the matrix, you multiply it by that, you take the dot product of that with a vector, and then you do the same thing, the second row, take the dot product with that. So with that, you write the matrix product, this times that, as you this vector. So let me take this vector 1, 2. Here I'm writing it as a row vector. So 1, 2 times, or dotted with 1, 2. That's going to be the first row of your answer. And then the second row is going to be 3, 4 dotted with 1, 2. So that's going to be the answer. And this is the same as, well, what's 1, 2 dotted with 1, 2 is the same as 1 times 1 plus 2 times 2. And then 3, 4 dotted with 1, 2 is the same as 3 times 4 plus, sorry, not 3 times 4, 3 times 1, 3 times 1 plus 4 times 2. So what does this give us? This gives us, here we have 1 plus 4, that's 5. And then here we have 3 plus 8, that's 11. So if we were to multiply this matrix by this vector, we would get 5, the vector 5, 11. Now, this is one way of looking at matrix multiplication, where you take dot products. But I want us to look at another way. This is not this is not my way. It is also another way of looking at it. That when you look at this result here, you can look at this column. Let me use a different color. So when you look at this column and you look at that column, what do you see going on? So here we have 1 and 2, and this 1 and 2, they are coming from this 1 and this 2. So we could have written this. Here we have the vector 1, 3 multiplied by 1, and then we have the vector 2, 4 multiplied by 2. So not only do we have this 1 and this 2, we also have this 1, 3 over here, and we have this 2, 4 over here. So that is interesting. If we dot 1 with this vector, so this is scalar multiplication, multiplying a vector by a scalar or a number is just the same as multiplying every entry of the vector by that number. So multiplying this 2, 4 by 2, we get 4, 8, and adding the 2, we get 5, 11, like we got before. So let's investigate this further, and let's do it in more generality. So let's start again. This time, in writing AX, I'm going to write AX A in terms of its components. So let's assume A has 2 rows and 3 columns. So we write A11 for the entry in the first row and first column, A12, A13. That means the entry in the A12 is the entry in the first row, second column. A13 is the entry in the first row, third column. And then we have A21, A22, A23. So this is, let me just for emphasis write, this is a 2 by 3 matrix, 2 rows, 3 columns. And let's take the vector. If we want this matrix multiplication to succeed, we need a vector with 3 components. So we have AX, and the question is, what is this going to give us? Here we want to do it in more generality. That is why I haven't put numbers for the entries of A. I've put just letters, unknowns, and we're just going to do the multiplication algebraically. So let's see. What do we do? Using the idea of dot products, we take the first row of the matrix, then we multiply by the entirety of this vector, right? So when we do that, we get A11 times x1, right? A11 times x1 plus A12 times x2 plus A13 times x3. Then we do for the second row, A21 times x1 plus A22 times x2 plus A23 times x3. So our result has 2 components, and this is how the 2 components look like. And again, I want us to notice what we noticed before, that if you look at this, what do you see? You see x1, x1 here. You see x2, x2 here. And you see x3, x3. Now remember where x1, x2, and x3 came from. They came from this vector. So what can we do? We can factor out x1 and x2 and x3 while thinking of these entries that are being added as components of vectors. So that's what we want to do. And when we do that, this is what we get. We get x1 times this vector, which we can call A11, A21, plus x2 times this called A12, A22, plus x3 times A13, A23. So what does that tell us? That tells us that we are multiplying x1 and x2 and x3, which we got from this vector. We are multiplying it by the columns of this matrix, because the first column of this matrix is A11, A21. So let me just, for emphasis, write this is the first column of A. Then this is the second column of A. And this is the third column of A. So to multiply a matrix A like this by a vector X, we are saying that it's equivalent to taking the components of the vector and multiplying by each column of the matrix. You take the respective components. So you take the first component, multiply by the first column, take the second component, multiply by the second column, take the third component, multiply by the third column, and you add them. And that is what this is doing. So that gives us a new perspective of matrix multiplication, or a different perspective of matrix multiplication. It's not just about taking dot products, it's also about multiplying the columns by constants and adding them together. We call that linear combination. So we take linear combinations of the columns of the matrix. So let's do another example. Let's say I have the matrix. Let's do a 3 by 3 matrix, our old friend. 1, 2, 3, 4, 5, 6, 7, 8, 9. Let's say we want to multiply this matrix by another matrix. Let's say 3, 2, 1. And we want to do it in two ways. We want to do it using the dot product. When we do it using the dot product, what do we get? We take the first row, that's 1, 2, 3. We dot it with 3, 2, 1. So we have, let's say, 1 times 3 plus 2 times 2 plus 3 times 1. Then we take the second row, we dot it with the vector. So what do we get? 4 times 3, 5 times 2, and then 6 times 1. And then we take the third row and dot it with a vector. So we get 7 times 3 plus 8 times 2 plus 9 times 1. So we see a nice pattern going on here. We have all threes here. Let me just circle all threes, all twos, all ones. And we also see 1, 4, 7, which is the first row of this. We see 2, 5, 8, which is the second row of that. And we see 3, 6, 9, which is the third row of that. So all of that is giving us a nice pattern that reinforces what we've been doing so far. But let's go ahead and simplify this. So what is this going to be equal to? Well, 1 times 3 is 3. 2 times 2 is 4. And then 3 times 1 is 3. So 3 plus 4 plus 3, that's 10. Then we have 4, 3, 12 plus 5 to 10, that's 22 plus 6, 28. Then we have 7, 3, 21 plus 8, 2, 16, that's 37 plus 9. 37 plus 9 is 46. So that's what this gives us using dot products. Now let's think about this in terms of a combination of the columns. So we are saying that this quantity is equal to what? It's equal to, we take the first component of that, multiply by the first column. So 3 times 147 plus, we take the second component, multiply by the second column, plus 2 times 2, 5, 8. And we take the third, multiply by the third column, we get 1 times 3, 6, 9. So we have a linear combination of 3 vectors. Now let's simplify and see what we get. If you multiply this vector, maybe I should write it here, it's going to be clearer. If I multiply this vector by 3, what do I get? I get 3, 12, 21. Here too, I get 4, 10, 16. And then here I get 3, 6, 9. And then I go ahead and simplify further. So here we have 3 plus 4 plus 3. That's 10. 12 plus 10 is 22 plus 6. That's 28. 21 plus 16 is 37. Plus 9 is 46. So this is exactly the result we got here. Same result using the two perspectives. So that gives us a little bit of insight as to what's going on when we multiply a matrix by a vector. But it shouldn't be it shouldn't be mysterious how these two methods are equivalent, because like I said, if you look at this result, what does it show us? It shows us that we have this 147, which comes from this matrix, and it's being multiplied by 3, and that 3 comes from this vector. Then we have 258, which is the second column of the matrix, which is being multiplied by the second component of the vector. And then we have this 369 being multiplied, is the third column, is being multiplied by 1, which is the third component. So that gives us the equivalence between the two methods, and another way to think about matrix vector multiplication. See you later.